Hello everybody. So we're still talking about the problem of the diffusion of reacting species in cylindrical and spherical catalyst. And here we will re-solve the problem with the changing of the boundary conditions. So these are the boundary conditions that we used to see, and we will see now the solution if we change the boundary condition to be at R equals R1, the flux equals negative Ks multiplied by CAS. So this is these are the boundary conditions. This is the main difference that we will apply. Again, we will equate the two equations, the flux equation and the C over R, and then we'll do the integration the same way, but in this case the integration is not limited integration, or we don't have limits of integration because this is not constant, the boundary condition, so we cannot do can do limited integration here. So we'll do the integration by adding an integration constant which is C2. We have two constants and we have two boundary conditions, so if I apply boundary condition number 1, so I can say that the flux equals negative KSCA, and C1 over R1 is the flux. We know that flux is C1 over R. At R equals R1, then this is gonna be R1. So this is the first boundary condition, which can translate into C1 equals negative KSCAS R1. The second boundary condition is gonna be the same. I'm gonna use the same equation, which is C1 ln R minus D CA plus C2, and I'll put the C equals C infinity, which is this, and put R equals R2, which is this, and this is the equation. I just put C1 with this value, which is this. I put C1 here, and this is C1. So C2 can be calculated in terms of all the rest of the parameters. Then I can take C2, C1 and substitute with them here, and the equation is gonna look like this. With some simplifications, taking common factors and all these things, you can get CA in terms of the rest of the parameters. And again, this is the concentration profile, and this is one difference here, is that I here was able to get the concentration profile. In the previous solution we got the flux. Of course we can use the flux to get the concentration profile, but still to get the concentration profile, but here you can get it directly. But still the same problem applies, is that I don't know the value of CAS, so in this case I have to do something. So the options that we have are limited, and this is luckily we have limited options, so that we don't get confused between the different options. So the two options that we have are the two boundary conditions. So if you apply the boundary condition of R equals R2 and C equals C infinity, then this term is gonna be ln R2 over R2, which is ln 1. So this term is all equals 0, which contains CAS, so you are not making anything useful, and it's gonna end up with CA infinity equals CA infinity. So you are not making anything useful out of it. The other option is to use or substitute with the values of CA equals CAS and R equals R1. So in this case, if you substitute, so this is the equation, you have CAS here, you have CAS here, so you can get CAS as a common factor and get CAS equals or is a function of all the parameters that we see here. So this is the value of CAS, which can be used or substituted with in this equation. So with some simplifications, you will find that this is the form of the equation. This is C as a function of all the other parameters. So it's kind of nice, and now we can get the shape of the concentration profile. This is something that we didn't do before, and I believe this is very useful to do this concentration profile, because it tells you a lot. And that's why I believe it's one useful thing is to try to get more out of the equation, not just to calculate something, but to see how the system behaves with the change of the parameters. So what I did is I divided the equation by C infinity. So I have C infinity here, I have C infinity here. So if you divide C by C infinity, then you have a concentration here that will have a maximum value of 1. So it's gonna have a very limited value, and the minimum value would be 0 if you have CA equals 0. It's not gonna be negative, of course. So it's gonna have C dash will have a value of 0 to 1. What I did is I plotted C dash, which is, I call here the normalized concentration, versus the catalyst radius. So I did the calculation. So the actual value of Ks is 2. So this is the actual concentration profile. So you see here it starts at C infinity, which makes C dash is equal to 1, and ends up at C AS over C infinity equals 0.27, 0.28, something like this. So this means that the reaction is not very fast or not very slow, so it's kind of having a concentration at the surface. But what I did is I resolved the same problem with the same givens using different values of Ks. So I used Ks from 0.02 and then 10 times 0.2 to 20 and 200. So, and I believe this is an amazing thing to see how the concentration profile changes with the speed of reaction. So in case of having very fast reaction at Ks equals 200, you'd see the concentration at the surface is 0, which means that or takes us back to the boundary condition that we mentioned earlier, that if the concentration or the reaction is very fast, then the concentration at the surface is 0, because once the species arrives and reaches the surface, it's totally consumed. So this is what we see here, that the concentration of A at the surface is 0 when the reaction is very fast. So it starts at C infinity and ends at 0. It gets higher when the speed of reaction gets or the K is smaller, which means that the speed of reaction is slower, of course. So you will have a fast reaction, but not fast enough to consume all the species A. So you will have higher concentration here, and it's gonna get higher and higher until you reach the point where the speed of reaction is very slow. You'll have a very slow or a very small concentration profile here, or concentration difference, which means that the driving force is very small. This is a very nice plot to see, actually, and I believe that it's not the only thing that you can get out of it, because the difference in concentration represents the driving force. So if you have more driving force, you will have more flux and you have more rate, and this is what we will see here. This is the profile of the flux, and by the way, this is exactly the same shape that we got from the previous solution. So it's confirming that we are on the right track. We're not producing something different. It's giving it different. It's getting the same output. And here you would see that this is the flux as a function of R. And then if you substitute with R equals R1, this is the equation. So if you want to plot the flux with radius for different values of Ks as before. So we have already seen the concentration profiles, and I want to see how this concentration profile will translate into, which is these profiles. I want to see how these profiles will translate into flux. So I should expect from my basic understanding and what we said earlier, that the rate is constant and R multiplied by N is constant. This is what the differential equation tells us, that R multiplied by N is constant. And as we go to the left, the radius, so this is R and N. So as we go to the left, the radius is getting smaller, so the flux will get higher. This is basic common sense. So I would expect that the flux curve would look like this. It starts small and then get higher. This is according to the equation, and this is what we see here, that N is inversely proportional with R, and we said that N is constant divided by R. So as the radius increases, the flux will decrease, and vice versa. And this is what we see here. You see here for the very fast reaction, you have the highest flux of all of the cases. And this makes sense. You have more driving force, you will have more flux. And this is what we see. You have a flux that is small, it gets higher until it reaches the maximum value at R equals R1. The same shape is almost for the case of K equals 20, which is a little slower reaction. And as you go down, the flux gets smaller, and the curve itself starts to look more like a straight line. And this is because you have very low flux, So the effect of flux on the or the area on the flux is not as significant as it is here. So you cannot see a very big. If you compare this with this and with this, you'd see that the increase in the flux here is very small. It's like if you compare this point with this point, you'd see it's a very small change in the flux, and this is due to, and this is important, this is due to the low driving force. You don't have very fast consumption of A, so you have a high concentration of A on the other side, so the driving force is not that much, so you have low flux, and that's why the flux profile is as you see. The interesting part is that if you can if you want to look at the rate, so the rate, we said it's n multiplied by 2 pi RL. I put unit length here, 2 pi is a constant, and if you multiply these two, R will disappear. So we have here R in the denominator. If you multiply n by this, which has R, then R will disappear, and this makes sense because rate is constant. So this is what I should expect, that has no dependence on R. So the rate for each one of these is constant, one of these, each of these lines. So I plotted the rate versus Ks. And this is what you see here, and this is amazing. You'd see that in this case, that for very low reaction rate or reaction constant or reaction speeds, the rate of mass transfer is very slow here. It increases as you increase the reaction rate until it reaches its maximum value at Ks equals 200. And this again, this has to do with the driving force. Higher driving force will lead to higher rate of mass transfer, lower driving force will lead to lower rate of mass transfer, and this is what we see here. So this is very nice thing that you can do, is to get any information from the equations that you get, check them, make sure that they make sense, and see how the outputs look like in reality, not just to have an equation and give the value and get done with this. So these plots are not in the textbook, so I believe this might be interesting to check here if you are interested. So this is all for the case of heterogeneous reaction. In the next video we will start with the homogeneous reaction. So I'll see you then, inshallah. Goodbye.